And thank you everyone for joining today's session. My name is Adam Arnold. I'm a product marketing engineer supporting Texas Instruments interface products. For this topic, we'll be talking about LVDS or low voltage differential signaling and multi-point LVDS portfolios. From this presentation, hopefully you'll be able to understand how and why LVDS is used, the breadth of different devices in TI's portfolio, and where to go to find more information on these two different protocols. But before we dig into more details on what LVDS and MLVDS are, I want to first start with an overview of differential signaling and the various different differential protocols that are commonly used. Then we can take a closer look at the LVDS and the MLVDS standards. TI has hundreds of devices in this category, so it can be daunting at first when selecting the right product for your design. So I'll spend a little bit of time discussing the different products that TI has and how to go about the selection process. And then lastly, I'll go over some of the best practices and considerations when it comes to implementing LVDS and MLVDS into your design. I think for today's presentation, I'll go through the slides and I'll save some time at the end where we can answer any questions. So in order to understand the benefits of LVDS, I think it's important to first understand the benefits of differential signaling. There are many differential signaling standards that are used in the market. So we'll talk about that in a later slide. But first, what is single-ended signaling? Well, single-ended signaling is the simplest form of communication, and it's the most commonly used way to transmit a signal. It consists of a driver, a receiver, and a single conductor that carries a signal that's referenced to some voltage. And oftentimes this voltage is ground. And so it has the advantage that it's very simple to implement, but it does have some drawbacks. The first drawback is that these single-ended signals are vulnerable to noise that's in the system. So that noise will couple to that conductor and be directly present at the receiver. The second drawback is that because it's referenced to ground, if you have ground shifts between your driver and your receiver, that will also be present in the signal, causing errors as well. And the last drawback is that it does generate a lot of EMI. Oftentimes, these signals are swinging from 0 up to standard logic voltages. So this could be 0 to 5 volt voltage swings, 3.3 or 1.8 volt. So it does generate a lot of EMI with these large voltage swings. All of these factors limit the speed and distance that you can transmit over these single-ended interfaces. There are some other protocols like RS-232 that have a wider voltage swing that enable you to transmit over longer distances, but they have their drawbacks in terms of data rate and other factors. So the solution to this is differential signaling. Now, differential signaling uses two conductors to transmit the signal as opposed to a single conductor. So on the driver side, it will transmit two complementary signals, an inverted and then a non-inverted signal. And at the receiver will take the difference between the two. And this has several benefits. The first one is noise rejection. So any noise that's in the system will couple to both the conductors. And so at the receiver will essentially subtract out the common mode noise and allow for much greater signal integrity. The second benefit is because the signal is not directly referenced to ground, there can be ground potential differences between the driver and receiver. Often cases, ground potential differences arise over longer distance transmission, or if you're transmitting between two different PCBs. It's important to keep in mind that it will depend on the differential receiver's common mode voltage that it can accept. And so this will be dependent on the standard. The next benefit is that it does have very minimal EMI. So current flows in equal magnitude in opposite direction. So what you actually get are coupled fields. And so EMI is very minimal with differential signaling. All of these benefits allow you to transmit at higher speeds or over longer distances with differential. I mentioned I'll talk to some of the different differential protocols that are commonly used, and they will vary in the different performance on data rate and distance based on their electrical characteristics. Before we get into that, however, I want to discuss the three modes of operations for the different bus topologies. The first bus topology is the simplest in nature, and it's point-to-point communication. This consists of a single driver transmitting to a single receiver. The next is multi-drop, where you have a single driver transmitting to more than one receiver. And the third is multi-point configuration, where the key factor here is that you have multiple drivers communicating over the same bus. Certain standards are better suited for point-to-point, and certain standards are better suited for multi-point and multi-drop due to the additional loading on the bus. And we'll talk about that a little bit more as we talk about the LVDS and MLVDS standards. So here is just a summary of the differential standards that I'm showing across the screen here. I won't go through all of the detail here, but it kind of contrasts some of the different bus topologies that are supported, the different data rates, cable lengths, power consumption, among other things. Today, we'll be talking again about the LVDS and MLVDS standards, and the main advantage that these standards have compared to some of the others that I have listed here is the balance of high data rate support, cable reach, and very minimal power consumption. And this is benefit for both the portfolios. And I'll kind of discuss on how this is supported as we look into the electrical characteristics of both. I'll start with LVDS. So again, LVDS stands for low voltage differential signaling. Essentially, it's a high-speed general purpose digital interface that's used for data, clock, or control signal transmission. The standard only defines the physical layer electrical characteristics of the signaling method, and it does not define the data link layer or other layers of the OSI model. So it's not dictating how bits are moving, rather just defining the voltages and currents to allow an LVDS driver to be compatible with an LVDS receiver, for example. And that is one of the nice benefits of LVDS is that it doesn't dictate any protocol on top of it. So it is very flexible in this nature, where you can define proprietary protocols or common protocols use LVDS as the physical layer interface. Now, let's take it one layer deeper into the electrical specification and how it actually operates. In the simplest implementation, LVDS consists of a driver, the transmission media, and a 100 ohm termination resistor close to the LVDS receiver. The driver consists of a 3.5 milliamp current source. That's a constant 3.5 milliamp current source, which is steered through some FETs. And so if I can annotate on here, if you have a logic high at the input, that will cause current to flow in this direction through the 100 ohm termination resistor and then back to ground. And so this will create a positive 350 millivolt differential voltage that's seen at the receiver. Similarly, if we have a logic low, that will cause current to flow in this direction through the 100 ohm termination resistor and back to ground, creating a negative 350 millivolt differential swing. Within the standard, it also defines the receiver threshold value of plus or minus 100 millivolts. Essentially what this means is if your differential voltage at the receiver is greater than 100 millivolts, then it'll result in a logic high output. And if the signal is less than 100 millivolt, or less than a negative 100 millivolts rather, there will be a logic low on the output. Because the differential voltage on the driver is 350 millivolts, you have plenty of margin compared to a 100 millivolt receiver threshold. So even though the differential voltage is very small, you got good noise margin through the electrical specification. The next component I'll talk to has to deal with the common mode voltages for LVDS. And I'll kind of direct your attention to the table in the bottom here. So LVDS drivers will output at a common mode voltage of 1.2 volts, whereas LVDS receivers can accept common mode voltage ranging from 0 to 2.4 volts. This allows for up to 1 volt ground potential difference between the driver and receiver that the receiver will be capable of accepting. So this is the feature that allows for that ground shift tolerance that I discussed on the earlier slide. All of these electrical characteristics, the very small differential voltage swing, lends itself to 3 key benefits. And the first one being LVDS's data rate and distance that you can transmit compared to the other differential standards I talked to. So LVDS is capable of transmitting in excess of 3 gigabits per second. Of course, this is very system dependent on the transmission distance, the tolerable jitter that you have in your system. And then you're also able to transmit up to 10 meters without any sort of buffering or redriving of the signal. And so, of course, these factors will apply to it, but you are able to get a good balance of data rate and transmission distance compared to some of these other standards such as RS-232, RS-422, and RS-485. The second benefit is in terms of power dissipation. The 350 millivolt differential voltage only comes out to be about 1.2 milliwatts of power dissipation, which is a fraction of the power of CML and PECL. And in the case of RS-422, it's over 30 times less power. And the last benefit is that even though differential signaling has great EMI performance, LVDS has even greater EMI performance with the small differential voltage swing. If you're curious to learn more about any of these benefits, TI has application notes on each topic that I've linked down in the bottom of each category to that report. So how is LVDS used? Well, LVDS is used most often for board-to-board communication. It enables you to have the benefits of differential signaling while being able to transmit at high data rates and very low power consumption. And so in most applications, this could be between 2 processors. This could be between a processor and a peripheral device, such as an ADC, a sensor, memory, and so on and so forth. Typically, This will consist of a LVDS driver that is used to translate a single-ended signal from your processor or peripheral device to LVDS, and then the LVDS receiver to translate that LVDS signal back to single-ended, which a ADC or microcontroller is capable of accepting. TI also has LVDS buffers in the portfolio that are used to repeat the LVDS signals, improving the signal integrity and reach of your LVDS link. In practice, LVDS is used across all markets, automotive, personal electronics. The left two examples are implementations where LVDS is used between FPGAs or microcontrollers. The top one is interfacing between an FPGA on a control board to an analog front-end board. This could be, for instance, an ADC on a front-end board that needs to transmit high-speed data back to a processor. LVDS is great for this because it offers the bandwidth needed and has great signal performance for board-to-board communication. It can also be used in the opposite manner to transmit clock or control signals from the control board to an LED module, for example. And so there are many different use cases that LVDS can benefits can be used for. Another application is using LVDS to transmit SPI or UART. In the instance of SPI, SPI was originally intended for an onboard interface over shorter distances, but as applications adapt, the need for transmitting SPI between boards or over longer distances has become more and more prevalent. And so the concern with this is transmitting this over single-ended SPI signals will have those drawbacks I discussed before. What we can actually do is implement each lane of SPI to differential LVDS using LVDS drivers and receivers. This will allow for that ground potential differences between the two devices. It will also allow for much greater signal integrity during transmission. One drawback and kind of consideration to keep in mind while implementing LVDS over SPI is that the maximum clock frequency that you can support through SPI depends on the round trip propagation delay from host to the target device and back to the host. So adding a differential transceiver in the communication path will add propagation delay and limit your maximum overall clock frequency. One of the benefits with LVDS is that it's very low latency compared to other differential standards. And so your propagation delay will be much lower compared to some of the others, maximizing the clock frequency that you can get. If you're interested, I also have a reference design that talks more in detail of implementing SPI over LVDS. At the end of this presentation, there will be a link for that. And then the last use case is for extending the reach of LVDS with buffers. And so LVDS buffers, as I mentioned, repeat the LVDS signal. They can also be used in multi-drop configurations to hide the effect of transmission line stubs. So I'll talk a little bit later about the different buffers that TI has in our portfolio. Okay. Now I will move to MLVDS. And as the name suggests, MLVDS is an extension to the LVDS protocol to support multi-point configuration. Again, similarly to LVDS, it's a new protocol defined by TIA EIA 899, and it just defines the physical layer electrical characteristics again. An important difference with multi-point configuration is that instead of having a single termination resistor, you now require termination on both ends of the transmission line. So here in the top right. So why can't LVDS support multi-point configuration? Well, the biggest concern with LVDS is the additional bus loading of added driver and receiver nodes off the transmission line. This will lower the overall effective characteristic impedance of the transmission line, and that, as well as the termination resistors in parallel, will decrease the load seen by your LVDS driver. LVDS's 3.5 milliamp current drive, large enough differential voltage based on the loading for a multi-point configuration. And so that's one of the differences that MLVDS makes, is increasing the nominal driver current to about 3 times that of LVDS to be able to support the additional loading on the bus. There are also other revisions to support a true multi-point configuration, such as edge rate control, bus contention provisions, and wired OR signaling. This is all implemented in the driver and receiver characteristics. I'll talk to a few of those differences now, but we do have more information you can learn on that. One of the main things is on the driver side. The driver does implement a wider offset range in common mode. So the drivers can have an offset ranging from 0 to 2.4 volts. In addition to that, the specification identifies the driver short circuit current. So the driver short circuit current won't exceed 43 milliamps. So that will limit your driver output voltage to a maximum of 2.4 volts, which is within the spec. Another feature of the driver is the transition times. The transition times are limited to a minimum of 1 nanoseconds, which it comes into play when you have transmission line stubs. I'll talk about that a little bit more in the design considerations portion. On the receiver side, the threshold voltages are, instead of being plus or minus 100 millivolts, are plus or minus 50 millivolts. So a little bit tighter of receiver thresholds. That, coupled with the additional current drive of 11.3 milliamp, increases your overall noise margin supported in MLVDS. The last feature is that bus pins for MLVDS receivers are ensured to be within 0 to 2.4 volts, and they're capable of accepting a common mode voltage range of -1 to 3.4 volts, and will allow for plus or minus 1 volt ground shifts between the different nodes in a multi-point configuration. Within the MLVDS spec, it also defines 2 types of receivers. The type 1 receivers are very similar to that of LVDS, where your receiver thresholds are centered around 0. Type 2 receivers, on the other hand, raise the receiver threshold voltages by 100 millivolts. So in the instance that your multi-point network does not have a signal being actively driven, your receiver won't be in an indeterminate state and will be in a known logic low output. This will make your system much more robust using a type 2 receiver. The second implementation with the type 2 is it enables you to operate in a wired OR configuration. So in the instance that you have multiple drivers on the multi-point bus and a receiver, if multiple drivers are transmitting high, this will result in a logic high at the receiver. However, if all the drivers are disabled at the receiver. And so it allows this type of configuration, which is often implemented for control types of applications. I'll talk to it as well, but all of TI's LVDS or MLVDS receivers and transceivers have an option for both a type 1 and a type 2. Now, the most common applications for MLVDS is in a backplane. So having multiple line cards that use MLVDS as the backplane interface, if optimized correctly, you're able to support up to 200 megabits per second in a fully loaded backplane with excellent signal integrity and minimal EMI. MLVDS is capable through the electrical specification of having 32 drivers or 32 transceivers communicate on a single bus. So typically this will be in a backplane configuration. However, it's also used for point-to-point communication. Because of the increased current drive of MLVDS, it enables longer distance transmission than that of LVDS at slower speeds. So if you need a higher speed alternative to that of RS-422 or RS-485, but need to transmit over longer distances relative to LVDS, point-to-point communication with MLVDS may be a good option. And that's what I'll discuss on the next slide. A little bit more is RS-485 is intended to be a high-speed, short-reach alternative to the RS-485 standard. A couple benefits that MLVDS has is, again, low propagation delay, much lower power and EMI relative to RS-485. Taking a look at the table on the right-hand side, you can see that across the different signaling rates, MLVDS has much lower power than that of RS-485. TI has devices for both portfolios, RS-422 and RS-485 as well. RS-422 and RS-485 will have a better noise of LVDS and is capable of transmitting over much longer distances. So if your system requires longer distances and not as high data rate, RS-422 and RS-485 might be a good option. But for each of our LVDS devices, we have pin-to-pin compatible RS-422 devices. And similarly for MLVDS, we have pin-to-pin compatible RS-485 options as well. It's not a direct drop-in replacement. There are some design considerations to keep in mind across the transmission length, type of cabling used, the termination, and the various electrical characteristics. So that was a quick summary of the LVDS and MLVDS standards. Now I'll share a little bit more on the different products TI has in our portfolio. So there are four main types of devices that we talked about a little. The first is driver. A reminder driver is used to take a single-ended signal such as CMOS or TTL, translate that to LVDS. A receiver is used to take LVDS signals and translate that back to single-ended. Transceivers consist of a driver and a receiver in the same package. And that comes in both a full duplex and half duplex configurations. And then lastly, buffers and repeaters that retransmit LVDS. I will also note that not supported under this portfolio, but TI also has LVDS signal conditioning devices that provide equalization for further improved signal integrity as well. The bottom table shows a summary across the different features and types of devices in both protocols, LVDS and MLVDS. On the LVDS side, we have many different devices ranging from various voltages, 5 volt, 3.3 volt, in cases down to 1.8 volt, various different signaling rates, channel counts ranging from a single channel all the way up to 16 for drivers and receivers. On the MLVDS side, most devices that we have in our portfolio are transceivers, and MLVDS coming in at a different number of channel counts, 1, 4, and 8. I recommend first finding the type of device that is needed for your design, and then narrowing down that search based on the different supply voltage requirements, data rate requirements, and any features that are needed. There are a couple features I want to highlight here, and I'll start from left to right. The first feature is the extended common mode range. So we have a receiver family of LVDS devices that support the common mode range of -4 to 5 volts. And so RS-422 and RS-485 standards have a much wider common mode, and this extended common mode devices give the look and feel of an RS-422 and RS-485 to LVDS. And so this supports longer distance transmission, or if you're transmitting in noisier environments, this extended common mode feature will help support that. The next feature is integrated termination resistors. So many of our LVDS receivers will have an option to integrate the termination resistor into the receiver. In the cases where you have 4 channels, 8 channels, or even up to 16 channels of LVDS, the option to integrate the receiver saves greatly on cost and board space. So that is indicated with a T in the TI part number. The next feature is receiver failsafes. So there are 3 ways to implement failsafe. The first one is just externally biasing the LVDS inputs to a receiver with a biasing network. And then we have a couple ways that it's integrated into the receiver. And this essentially will allow the receiver to have a known output when either the receiver is disconnected or the driver is disconnected in those unknown states. I'll note the active failsafe feature, which is a part of our SN65 LVDS3 families. This part implements a window comparator that monitors the threshold of the input of the LVDS receiver. And if it drops beneath a threshold voltage, it will then toggle the output. And if that stands for a period of time, it will then toggle the output in a known logic low. And this is the best implementation for failsafe because it doesn't alter the electrical characteristics or the common mode voltage of other failsafe networks. The next feature is we have devices that support high ESD, so 7 kV plus HBM. And lastly, devices, special feature products for fan-out buffering. So these devices have an LVDS input and are used to fan out to multiple LVDS outputs. So this could be in the form of a single LVDS input fanned out to 4 LVDS outputs, or even up to 16. This is typically used for clock distribution or data distribution throughout a system. We also have other special feature devices like crosspoints that can be used either as a direct buffer, a mux, or a switch. So there are some other special type of features. I recommend starting with the TI selection guide here. This highlights the key devices that TI would recommend for the different device functions, the different channel counts. It also highlights across LVDS, PECL, which I won't talk to in today's presentation, and MLVDS. It'll also highlight in the corner the different features that I discussed on the previous slide, and any TI rating as well across automotive, enhanced plastic, and QMLV space. I will highlight on this slide that we do have a new device that we're continuing to invest in the LVDS portfolio, and we released DS90 LVRA2, which is a first to market 1.8 volt LVDS receiver. And that is a common question that we get, is how to enable LVDS for low power FPGAs and processors. It's very consistent throughout the market that FPGAs and processors are scaling back their core voltages, and with that, they're scaling back their I/O voltages. And so instead of natively supporting 3.3 volts, now the I/O voltages are dropping to 2.5, 1.8, and even as low as 1.2 volts. So the way you can implement this, instead of configuring the full I/O bank to support a higher voltage and sacrifice on processor performance, is to implement a level shifter along with the LVDS devices. And so I have this table below that highlights some of those level shifters that can be used directly with LVDS to support a wide range of voltages. This could range from 0.65 volts all the way up to 5. There are some drawbacks with this approach. The main drawback is that it will increase the component count in the board space implementing the level shifter. It'll also limit the data rate in which you can transmit LVDS to that which is supported with the level shifter. And so that's the benefit of the new 1.8 volt LVDS device, is that it will inherently support 1.8 volt supply and logic voltages without the need of using a level shifter. Again, that's supported with DS90 LVRA2. To talk about a little bit on the packaging, TI has many different options for the channel counts on package options, continuing to invest in industry standard packages that are multi-sourceable, but also new package options that are very small as well. So that is one example on the new DS90 LVRA2 device, is in a very small 2x2 DEM package. So over time, continuing to invest in the smaller package options. Okay, so some design considerations for starting with LVDS. When implementing LVDS, PCB traces should be 100 ohm characteristic impedance. It's also important to maintain equal length and symmetry between the differential traces to avoid any inter-pair skew that could be added. If possible, minimize trace lengths as much as you can and minimize the use of vias. TI recommends less than 2. In addition to that, it's recommended to use a continuous ground plane under the differential traces. Of course, avoid routing with right angles. Don't route near the edge of PCBs or any near noise sources such as oscillators or switching regulators as well. For the MLVDS devices, it's important to keep in mind for a backplane type of environment, the slot pitch. And so the closer the slot pitch, the larger capacitive loading that you will have. And so TI will recommend 2 centimeter slot pitch, as well as evenly spacing the loads throughout the multi-point bus. Typically, MLVDS can support up to 32 nodes on a single bus, but this is very system dependent on this layout, proper termination, and stubs. And so I'll talk to stubs a little bit more here. And so stubs are the connections to the multi-point bus from the different nodes. It's possible to minimize the effects of stubs by minimizing the stub lengths as much as possible. It's recommended to keep the total propagation delay of the stub less than 30% the rise and fall time of the MLVDS driver. And so this goes back to the benefits of MLVDS defining the transition time to have a minimum of 1 nanosecond. This essentially allows for more flexibility in the length of the stubs off the backplane. So to take a look at an example on the right-hand side, you can gather the rise and fall times from the datasheet of your MLVDS driver. In this case, 1.5 nanoseconds. Using the rule of thumb of less than 30% the rise and fall time, that would mean your stub length would need to be less than 0.5 nanoseconds. For FR4, this would indicate a stub length of less than 3 inches. If you were to use a standard like LVDS for multi-point, your rise and fall times are much faster, which enable higher data rates, but that would severely limit the stub lengths that are supported for multi-point. And so MLVDS just gives that additional flexibility within the standard to have longer stubs. But if you can, it's best to have minimize the effects by making it as short as possible. Another consideration for MLVDS is selecting the characteristic impedance of your transmission line. Plug-in boards on the backplane can add capacitance from stubs, the different transceivers, connectors, vias, and essentially will lower the overall effective characteristic impedance of the bus. So it is recommended to select a characteristic impedance that's actually greater than 100 ohms. So that way that the effective characteristic impedance remains over 80 ohms. So in the instance on the right-hand side, the characteristic impedance of this loaded backplane is 130 ohms, but the effective characteristic impedance is 80 ohms, and that's why the termination resistors are selected to be 80. And that's a quick summary of the different considerations when designing with LVDS and MLVDS. If you're looking for more information, please visit ti.com. You can use the ti.com /cross-reference search to find crosses for TI products. You can enter a single part number in the search box, or you can upload a file of multiple devices and find the correct crosses. To find more information about LVDS, you can go to ti.com /LVDS, or go to the homepage, select products, go to interface, and then find LVDS and MLVDS in the top right hand. The ti.com product page has a lot more information on the different devices that are recommended across the different features. It also has different application reports and blogs for more information. I've highlighted some here as well. The LVDS Owner's Manual and the LVDS Application and Data Handbook are great places to start to get more information from the very basics of LVDS, detail on the design consideration side. We also have some great TI Precision lab videos to learn more as well. With that, I think I can open it up for some questions. I think we have a little bit of time.